Hello students, welcome to Maths 1325 Applied Calculus. Lesson 0 covers preliminaries, so if you feel comfortable, just skip it and go over to Lesson 1. If you do decide to stay here, then please remember you can study this topic or entire lesson, skipping any topic you like and jumble the order in any way you like. These are all independent topics from preliminary materials from several prerequisite courses. Section 1, they're mainly about selected topics from pre-algebra and basic algebra. Section 2, selected topics from intermediate algebra and advanced algebra. Advanced algebra, I mean by either college algebra or business algebra or algebra for teachers or STEM algebra, whatever algebra in college level. Now for geometric preliminaries, lines were essential and we went through many times in various courses, including algebra classes. And then circles and crossing points, I'm not so sure if they are really important, especially circles. In trig-based classes, of course, they are important, but I'm not so sure. Now here, let's talk about 3.4 additional topics. And one is Pythagorean theorem. So whenever you have right triangle, hypotenuse squared is the sum of the squares of the other two sides. A squared plus b squared is c squared, as you can see. That's a right angle. And let's see. Let's talk about the proof briefly. Okay, sketch of proof. Here's one method using the complete square formula. Anybody remember this? So, put this right triangle in a clever arrangement like this. 1, 2, 3, 4 of those. Then the hypotenuse forms a square. So that square, the blue square, has area c squared. How about this big rectangle here? That's a plus b squared. A plus b in horizontal and vertical as well. And then we have this 4 red right triangle. So 4 times the area, 1/2 AB. So we get this equation by looking at the areas. All right? And then you can work out algebraically. This complete square, you can break it down as a squared plus 2ab plus b squared. And the right-hand side is c squared plus 2ab after simplification. And further simplification, you get a squared plus b squared equal to c squared because this plus 2ab and that plus 2ab would cancel each other out. So it's coming from a single picture like this. Another way to do the same thing, another complete square method, but this time instead of arranging like this big, arrange a little bit different way. This time the big rectangle is the rectangle or square given by the hypotenuse, so that's c squared. And then how about the green square down here? That's a minus b squared. A is big side, b is smaller, so a minus b. So that's each of them, and that 2 is a minus b, that's a minus b, that 2 is a minus b. You see a is from here to there all the way, and b is from here to there. A you get from the triangle down here, b you get from triangle from here, so it's a minus b squared. So we have the a minus b squared, the green area, plus the 4 areas, areas of 4 rectangles, 4 times 1/2 AB is equal to c squared, and then you algebraically manipulate a squared minus 2ab plus b squared, and a plus 2ab from this red. So these two cancel each other out, and you get a squared plus b squared equal to c squared. Here's another argument. Again, let's look at the area. Area of the green triangle plus area of the red triangle should be the area of the big triangle. And the area of the green triangle must be proportional to a squared because area is two-dimensional quantity. See? So that's why proportional to square. And then this red area is going to be proportional to b squared. Again, the area is two-dimensional quantity, and this is side. This is one-dimensional, so we need square. And this one, c squared. See? For green triangle, A is hypotenuse. For red triangle, B is hypotenuse. For big triangle, C is hypotenuse, and they're all not congruent. They're all similar. So add them all up, and what do you get? Ka squared plus kb squared is equal to kc squared, and k's cancel out. You get Pythagorean theorem. And I went through several ideas, but they all point toward the same thing. We looked at areas, and there are other proofs as well, but most of the proofs, including the original proof by Pythagoras, they all require some kind of argument on areas. Okay, so much for Pythagorean theorem. Now let's go to some 2D figures and their areas. Easiest is a rectangle. Area is A times B, and that's where everything started. As a matter of fact, if you arrange some boxes or any objects and then do some counting, then you end up with horizontal times vertical. The detail is left to you. And triangle is 1/2 AH, where A is base and H is height. The same applies for obtuse triangle, and the proof actually follows from the observation that area of the triangle actually is half of the area of the rectangle given by this base length, and H height. Form like this, and then this left-hand side right triangle and this white right triangle, they are the same. And then this right triangle, the thin one, and this right triangle, the white one, and the dotted point, they're the same. So this big rectangle has twice the area of this triangle we are looking for. So find out the area of the rectangle and take the half. Then you get the triangle area. That's why we get 1/2. For obtuse triangle, it's kind of similar. I mean, I'm looking for this pink. Yeah, this one. And then if you go with this right triangle here, then you'll see that A plus B times H. 1/2 A plus B times H will be this area. And this is acute triangle, so it works. And then subtract away this green B. And then what do you get? Well, algebraically manipulate, break up this parenthesis, and 1/2 BH, 1/2 BH cancel each out. And then you end up with 1/2 AH like that. Another way to do something similar is to form a parallelogram and working out. So that is, let's see, doing something like this. Kind of like this. So do not consider this green part. Just look at this parallelogram and note that the area of this obtuse triangle is half of the area of the parallelogram. And it'll turn out the area of the parallelogram is A times H. So half of that, 1/2 A times H. That's another way to do it. But here, I didn't do the parallelogram yet. So the previous method will have to work. Okay, next, let's go to parallelogram. So area is A times H. How do you do that? It turns out that if I cut this much, this triangle, and then paste it over here and form a rectangle, then the area of that rectangle and the area of the original parallelogram must be the same, because all I did was just cutting and pasting. And the area of the rectangle, that's A times H. So you have the area of parallelogram. How about the area formula for trapezoid? It'll turn out that its area is 1/2 A plus B times H, where A is up and B is down, H is the height, where A and B, those two sides, are parallel to each other. And the proof, well, here's the proof. Get another copy of the same parallelogram, no, not parallelogram, trapezoid, and the result is a parallelogram. So the area of the original trapezoid, this blue trapezoid, must be 1/2 of the area of this parallelogram. And what is it? The base length times height. That's how you get the area of the parallelogram, but this is base length of A plus B. So A plus B times H, but I need half of that. That's how you get the area of the trapezoid. Finally, the circle. That's much trickier. You can cut those like pizza pie and then rearrange like this. And looks like kind of parallelogram, but cut further and form like this, and cut further and form like that, and cut further and form like this. And as you can see, as you cut more and more and more, this resembles rectangle, and then the height gets closer and closer and closer to the radius, and then this base length is actually half of the circumference. So the circumference stays half of the circumference. So circumference is 2 pi r, is it? So just pi r times another r, so pi r squared. So we have 2D figures, and do we have time for some 3D figures? I don't know. For any kind of box. And the volume is AB times C. So AB is the area of the bottom, base area, times height. So that's the volume. The surface area is trickier, but you can figure it out if you draw a net. So bottom area of AB, top area of AB, and side area of AC, and side area BC, you see, A, B like that, and then height is C. And then if you draw this in a paper and cut through and then fold over, then you can retrieve this box. And from this kind of argument, you can get all the surface areas. Circular cylinder, volume is pi r squared, that's base, times height. So yeah, base area times height. But what about the surface area? Well, this is a side, and that's a top circle, and that's bottom circle. So top and bottom circles, those are pi r squared. There are two of them. That's the radius. And then how about side rectangle? Height is here, and then the width actually will have to match the circumference of the top and bottom circles. That's why we have 2 pi r times h. So that's how you get the surface area for circular cylinder. Circular cone. Oh boy, that's harder. Circular sphere and ball. Getting worse and worse. Polygonal cylinder. Polygonal cone. Well, I'll leave the details to students. Getting worse and worse and worse.